All right, so hello everyone. I guess we are live now, and welcome you all to GFG channel. And there's a post analysis session of the last weekly contest 187. So let me check if I'm audible. So just write a quick +1 if I'm visible and equally audible to you. Okay, was not able to solve any question. Okay, that's totally fine. So we'll discuss all the problems in very much detail, and there is no prerequisite for any problem. Cool. So let's just start with the first problem. And I personally categorize this entire contest from easy to a medium level. And all the problems were based on some intuition, and all the problems are ad hoc problem. You just have to draw some constructive algorithms, and that's enough to solve the problem. And moreover, it's on a bit combinatorics and mathematics side, but not that much hard so that you cannot figure out. Anyways, let's just get started with the first problem. Okay, sure. So hope my screen is visible to you all. So let's just start with the first problem. And also let me just change the template. So yep, this one seems good to me. So the first problem, find nth term. So in this problem, you are given a recurrence relation. This is a fairly easy problem. So you are given a recurrence relation and you need to find the nth term of the sequence. And this is the following recurrence relation. And the nth term can be very large, so you need to print the answer under modulus 10 power 9 plus 7. And these are the two base cases. F of 1 is equals to 1, f of 2 is equals to 1. These are the two base cases we have. And the value of n can be up to 10 power 5 only. So this simply means I can iterate over all the integers from 1 to n. So let me just first write the recurrence relation. So f of I, we all know the base cases. F of 1, this is simply equals to 1. F of 2, this is also equals to 1. So let's just create an array f of size n plus 1. Now here I have two base cases. F of 1 is equals to 1 and f of 2 is equals to 1. Then after this, simply iterate over all the possible values of I. So for I is equals to 3, start from 3 and it goes till n. That's why I have created an array of size n plus 1. Then my recurrence relation f of I is simply equals to I multiplied by f of I minus 1. Then minus I minus 1 and multiplied by f of I minus 2. I minus 2. Cool. And then I need to add plus I minus 2 and multiplied by 3. So let me write this term also here. So plus I minus 2 and multiplied by 3. This is the recurrent solution, and you can find this value for every I. And finally, your answer is simply equals to f of n, the nth term of this sequence. But there is an edge case that you have might miss. We need to find this answer. We need to find this answer under modulus 10 power 9 plus 7. So under modulus 10 power 9 plus 7. So let's call this as mod. And the value of mod, this is equals to 10 power 9 plus 7. So you might have missed one edge case. It might be possible when this term value exceeds the integer limit. So if you exceeds the integer limit, so we have to immediately take the mod. Otherwise, you will get some wrong result. So in my implementation, I called this term as the first term. This is my first term. So first I will find the value of this, because the value of n can be up to 10 power 5, or it was 10 power 4. Let me just quickly check. It was 10 power 5. So the value of n can be up to 10 power 5. So consider the case when the value of I is around 10 power 5 and f of I minus 1. This is exponentially growing. So consider the case when it is f of I minus 1 is close to 10 power 9. So in that case, if you multiply these two terms together, then your result is 10 power around 10 power 14. So it cannot be fit in integer data type. So I must have to take the mod, and that's why in my implementation I have divided this entire expression into three terms. So first I will find the value of first expression, then this is the value of second expression, and this is the value of third expression. And after finding every term, I will take a mod. I will take a mod with this mod, so that my answer never exceeds the integer limit. So yeah, this is the complete solution for the first problem. And here we have implementation. This is the complete implementation of the first problem. This is the function that you need, method that you need to complete. Then here I have my mod. Then f array. These are the two base cases. Then I iterate over all the possible values of I from 3 to n. And then this is my first term. Then this is my second term. I am subtracting the second term from the first term, and make sure to add mod if you are subtracting this, because the values might be negative. So I am adding this mod to get the positive remainder only. This is the very basic principle of modular arithmetic when we apply to the negative numbers. So plus mod, and then again take a mod, and finally I will add the third term f of I plus this third term, and my answer is simply equals to f of n. So is it clear to everyone? Just write a quick plus one if the problem is clear to you. It was super easy problem. The time complexity is linear, space complexity is also linear. Everyone quickly write a plus one so that we can discuss the next problem. Yes, you can say this is DP because we are using the answers of the previous state. So count n digit numbers. Yes, you can also solve this problem by using two variables, because for every by using two variables, because for every state I just only need to know f of I minus 1 and f of I minus 2, f of I minus 1 and f of I minus 2. So why to store the answers which are previous to this f of I minus 2? So this problem can also be solved by using two variables. In that case, the space complexity would be constant. So this is an homework task for everyone. Just implement this problem and try to solve it using two variables, two or three variables. I just only need to know the answer for the previous two terms, values of two previous terms. So the value of n can be up to 10 power 5. So you cannot use recursion. Otherwise, the time complexity would be 2 power n. This is exponential and it won't be able to pass all the test cases. So you will get a time limit exceed error. Verdict: time limit exceed is not an error, it's just an status that you haven't solved the problem under the given time limit. Anyway, let's just move to the next problem. So count n digit number. You have been given an integer n and you need to find the count of n digit numbers formed using digit from 1 to 9 such that the GCD of the digits is greater than 1. And this statement is very important. The GCD of the GCD of the digits of the number must be greater than 1. We don't have to care what is GCD, but it must be greater than 1. And since the answer can be very large, so you have to print the answer under modulo 10 power 9 plus 7. So let's just quickly discuss how we can solve this problem. Count n digit numbers. So count n digit number. So we have 9 digits from 1 to 9. So digit 1, digit 2, 3, 4, 5, 6, 7, 8, and 9. And we need to form a number whose length is n. And basically we have these digit in a number, and the number of digits would be n. And the GCD of their digits must be greater than 1. So let's just break this thing into a multiple cases. But before this, I just want to give you a quick reminder that GCD of a comma b, GCD of a comma b is always less than or equals to minimum of a comma b. For example, let's say we have a GCD of 4 comma 12. So the GCD of 4 comma 12 is simply equals to 4. Now what is the GCD of 3 comma 6? So the GCD of 3 comma 6 is equals to 2. Is equals to 2. Or sorry, it is 3, not 2. It is equals to 3. So the GCD of a comma b is always less than or equals to minimum of a comma b. But there is an edge case. There is an edge case provided this a and b must be greater than 0. So if and only if A not equals to 0 and B not equals to 0. B not equals to 0. Because if any number is equals to 0, let's say GCD of 0, 6. So in this case, your GCD is simply equals to 6. So, and if it is non-zero, then it is always less than or equals to minimum of A comma B. Cool. So I have to form a number with the n digits, right? And these many digits I have. These many digits I have. So, and after this, I need to take the GCD of digits, GCD of the digits, and this GCD must be greater than 1. So this GCD must be greater than 1. I do not need to care what is the GCD value, but it must be greater than 1. Cool. So I know the GCD of our digits is always gonna be less than or equals to 9, because here the maximum number that we have is 9. So if you take a GCD with a 9 and any other number, then it's obviously gonna be less than or equals to 9. So I hope it is clear to everyone. Now let's just find the GCD and break this thing into a multiple cases. So let's just write a case 1. So case 1, here I am going to count the number of count the numbers where we have n digits and a GCD is multiple of 2. So count n digits numbers whose GCD is a multiple of 2. Multiple of 2. So I don't care what we have the actual GCD value, it must be greater than 1. So if I know the count of n digits number, if I know the count of n digits number whose GCD is a multiple of 2, then I can increment my answer by that value. So what are the multiple of 2 we have? So the multiple of 2, which is less than or equals to 9, are 2. 2 is a multiple of itself. 2 is a multiple of itself. And then we have 4. Then we have 6. And then we have 8. So yeah, then we have 8. And if you select any combination of these 4 digits, then the GCD value that you will get is always the multiple of 2. I don't care what is the actual GCD, but it is always the multiple of 2. So how many such numbers we can form? So I have to fill n positions, right? I have to fill n positions. And for every position, I have 4 options. Either I pick 2, either I place 2, or I place 4, or I place 6, or I place 8. So for every position, I have 4 options. So isn't it 4 to the power n? 4 to the power n. I have 4 options. This is super simple. I have 4 options for every option. For every position, I have 4 possibility. So that's why it is simply equals to 4 to the power n. So I hope this thing is clear to everybody. Now let me write the second case. So this case 1 has covered all the possibility. This case 1 has covered all the possibilities when the GCD is 2, when the GCD is 4, when the GCD is 6, when the GCD is 8. This case 1 has covered all the possibility when the GCD is 2, when the GCD is 4, when the GCD is 6, when the GCD is 8. Now, let me write the case 2. So, case 2. So, in case 2, I will count the n digit numbers whose GCD is a multiple of 3. So, case 2, count of n digits number whose GCD is multiple of 3. Multiple of 3. So what are the numbers we have which are multiple of 3? So it is 3, 6 and 9. So I have n options. Again, I'm using the same idea. I have n positions, and if I want to have a GCD as a multiple of 3, then it must be filled with these 3 values. It must be filled with these 3 values. So what will be how I can increment my answer by which factor? So this is simply 3 to the power n. For every position I have 3 option. This position I have, for this position I have 3 option. This position I have 3 option. For this position I have 3 option. So for every position I have 3 option and I have n such positions. So this is simply equals to 3 to the power n. This is simply equals to 3 to the power n. So let me just change the color. 3 to the power n. And now I have covered all the cases when the GCD is 3. I have covered all the cases where the GCD is 6. And I have covered all the cases where the GCD is 9. But here you can notice one thing. I have covered this 6 wala case twice. So I have to subtract the contribution of 6 one time because I have added this contribution of 6 twice. So now tell me guys, how many number are possible with the n digits and GCD of the digits as 6? There is exactly one number. So if at all the n positions, if at all the n positions you have 6, then only your GCD will be equals to 6. So 6, 6, 6. When at all the position we have 6, then the GCD of a 6, 6, 6 is simply equals to 6. So there is only one case when the GCD is equals to 6, and I have added this case twice. So I need to subtract 1. I need to subtract 1. This is an edge case. So subtract, let me write it this way, -1. I need to subtract this case. So -1. So now I have covered this 6 wala case exactly one time. Now what we are left with? Now I need to know the number of the count of numbers where the GCD is 5. The GCD of the digits is 5. So let's call this case as 4, case 4. So count of n digits, count of numbers, n digits number whose GCD is 5. So GCD as 5. So there is exactly one possibility. Yes, exactly one possibility. When I place all at all the position, if I have 5, then and only then GCD will be equals to 1. So there is only one possibility. Only one possibility. Now similarly, let me write the case 4. This was case 3rd. So case 4. case 4, when we have GCD as 7. So again, only one possibility. So only one possibility. When at all the places you have 7. If at all the places you have 7, then 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 and only then GCD is equals to 7. So only one possibility. Only one possibility. So now let's just finalize and summarize everything. So my answer. So now I have covered everything. I have covered all the cases when the GCD is 5. I have covered all the cases when GCD is 7. Cool. So my final answer is equals to 4 to the power n and plus 3 to the power n minus 1 plus 1 and again plus 1. So I can simply say my answer is equals to 3 to the power n, 4 to the power n and plus 1. So is it clear to everybody? Just write a quick plus 1 if this thing is clear to you. This formula. How I come up with this formula. So let me just show you the implementation. So here is the implementation of the second problem. This is the method that you need to complete count numbers for a given n. So this is my mod 10 power 9 plus 7. So here I have written this power function to find the value of a to the power b under modulus mod. So this power function uses a binary exponentiation, but since the value of n can be up to 10 power 4, let me just quickly check what is the possible values of n. So the value of n can be up to 10 power 4 only. So that's why you can also write the naive approach to find the value of a to the power b. But here I have used binary exponentiation, using which you can find the value of a to the power b in just log of b base 2 time, but not required. So my answer is simply equals to 4 to the power n plus 3 to the power n and plus 1. Cool. And make sure to take a mod here, and then I will just simply return this answer. The time complexity here is log of n base 2, or in case if you are writing the brute force way of finding the power, then the time complexity is linear, and then also it will pass all the test cases. Yes, Karthik, you can also use inbuilt functions, but inbuilt functions are not reliable for the some cases. Because internally the inbuilt function POW, POW, inbuilt function POW uses the data type double, which might causes some precision and accuracy error. Yes, Ankush, you can solve this problem with the DP, using DP also, as the value of n can be up to 10 power 4 only. So try to use this power function, modular exponentiation. Karthik. So let's just move to the next problem. This was also a very interesting problem, and this is a this is a greedy problem. So let's just go for it. Maximum possible bitwise add. So here you are given an array, integer array ARR of size n and an integer k. You have to select exactly k different subarrays from array ARR, and for each selected subarray, calculate the sum of its element. Then compute the bitwise AND of these sum, and you need to return the maximum possible value of a bitwise AND. Then here we have a definition of a subarray. It is a continuous segment of the array. So let me just again quickly summarize the problem statement. So you have an array of size n, and you need to select k distinct subarrays such that the bitwise the bit the sum the bitwise sum the bitwise and of their sum is maximum, and the value of n can be up to 100, and the value of k is obviously gonna be less than the number of subarrays that we can make. So let's just discuss how we can solve this problem. Maximum possible bitwise add. So the very first thing is the constraint. This is the foremost important thing to solve any problem. The value of n can be up to 100, and the value of k is less than or equals to n multiplied by n plus 1 divided by 2, and which is equals to the number of subarrays. So total number of subarrays for any array with the size n is equals to n multiplied by n plus 1 and divided by 2, and so obviously k always must be less than or equals to this count, this total subarrays. So how we can solve this problem? So let's just first generate all subarray sum and store in an array. So this is the first step. First I will generate all subarray sum subarray sum and store it in an array. Let's call this array as s array s, and then from this array s I need to pick k elements such that their end value is maximum. And how you can generate all the subarray? This is very simple. Just use a to loop. I starts from 0 to n minus 1, and j starts from I and goes till n minus 1. So using to for loop, you can generate all the possible subarrays. So I'm not going to discuss this thing as it is very basic. So thereafter, I need to pick k elements. K elements with maximum with a maximum and value. Maximum and value. Now we can think greedily. Now we can think of a greedy solution, because the leftmost bit is having the maximum bit. So we try to pick all the bits, all the elements whose leftmost bit is set. So let me just explain you with some example. So let's say we have S0, and here I'm going to write the binary representation of element S0. So let's say this is 1, then 0, then 1, then let's say we have again 0, then we have 1. So let's say this is my bit 0, this is my bit 0, then bit 1, bit 2, bit 3, and bit 4. So here the idea is to use a grid. You gridly select the values. I want to set this leftmost bit in my answer, and I have initialized my answer with 0, as initially I have not picked any element. So I will initialize my answer with 0. So let's just also write the binary representation of the answer. So we have 32 zeros if you are using integer, or in case if you are using long then the 64 zeros. So let's just for explanation purpose, I'm going to write only 5 bits. So 0, 0, 0, 0, and 0. So this is bit 0, bit 1, bit 2, bit 3, and bit 4. And I want to set the leftmost bit so that we have the maximum answer. So let me also write some more elements. So let's say we have S1, and let me just write the binary representation of this S1. So let's say we have 1, then 0, 1, 1, and 0. So let's say we have then we have S2. So here let's say we have 0 and 3 times 1, and then again 0. Then let's say we have S3. Then for this S3, let's say we have 1, 0, 1, 0, and let's say we have again 0. Then S4, 1, 1, 1, 1, and let's say that we have 0. Now, is it fine to have 5 elements? Actually, it is fine for explanation, but it is not possible to have 5 subarray, 5 distinct subarray. We must have this number. This number is always even. You always have an even number of subarrays. This number is always even. Cool. Or maybe it is odd. So let's just not go for this case. It can be odd also. So just forget about this previous statement. So let me just quickly draw one more element, S of 5. So here we have 1, then 0, 0, 1, and 0. Now what is the maximum value that I can generate from these 6 subarray sum? Maximum AND value that I can generate. So already discussed, as I have already discussed that we want to have the leftmost bit as set. So I'm trying to have a I'm trying to pick the elements whose bit 4 is set. So what are the elements here we have whose bit 4 is picked, whose bit 4 is set. And definitely I will iterate from left to right, because the leftmost bit is having the maximum bit. So I will give the priority to the bits in a order from left to right. So, and also let's say the value of k is equals to 3. Value of k is equals to 3. That is, I only have to pick 3 elements from this array S. So to have this bit 4 as set, what are the options I have? So either I can pick this one, these 3 elements, or I can pick any combination of these 3 elements. These 5 elements. Among these 5 elements, I can pick any 3 element. Then their AND value will be set in my answer. So let's just decide which 3 values I will pick. So one thing I'm 100% sure, if the count of elements, now please try to pay more attention, if the count of elements whose bit 4 is set is greater than or equals to k, then it is possible to have a bit 4 set in answer. And if we have a count less than k, then it is not possible to have bit 4 set in answer. So here we have five elements whose bit 4 is set. So this element, this one, then this one, and this one. So I will select 3 elements among these 5 elements. I will pick 3 elements among these 5 possibility. So which 3 elements I will have to pick? So let's just do not decide at this moment, because I know I can make this bit set in my answer. So I do not care which values I will pick. But one thing I am 100% sure, one thing I can claim 100%, that I'm never going to pick this index 2, this s of 2, because it has 0. If you pick this element, then you cannot have a bit 4 as set. And since it has the maximum weight, this is 2 power 4, it this bit has the maximum weight. So I will give a priority to this bit. I will try to make this bit as set in my answer. So I know I'm not going to pick this element anymore, because it does not have bit 4 set. No matter whether the upcoming bits is set or not, I definitely not going to pick this S2. So let's just delete this S2 from here. Here I'm going to delete this S2. Do not get confused. I will discuss how you can implement this. But at this point of time, let's just focus on the on the approach. So now, currently I'm having 5 elements under the consideration. Now let's just move to the next bit. And before moving to the next bit, I will make a mark this bit as set. It is possible to have this fourth bit set in answer. So now the next bit, which is a 3. So here I will check how many numbers we have whose bit 3 is set, and these numbers are going among these 5 elements. So here how many numbers we have? So here only we have one number. We only have one number. We have only one number, one element whose bit 3 is set, and this count 1 is less than 3. So from here I can simply say it is not possible to make bit 3 set in answer, because we do not have a at least 3 elements, at least k element. So it is not possible to have this bit as set. Cool. So let's just skip this bit. Here I'm not going to delete any element. Now I'm going to simply skip this bit. It is not possible to set this bit 3, because to have a bit, to set the bit 3, we must have at least k element, which is not here. Now let's just move to the next bit, which is 2. So how many elements we have set? We have this bit set. So this is S0, then S1, then S3, S4. So we have 4 elements, and this count is greater than or equals to k, which is 3. So we can have this bit, I can make this bit a set. Cool. So I can make this a bit set. So let's just mark this bit set in answer. And then, can I claim something? Yes, definitely I can claim something. This S of 5, this S of 5 has bit 2 as 0. So I will not select this one. I will not select this one in future. So let's just delete this element S of 5. Let's just delete this element S of 5. So I will delete this element. Cool. Now let's just move to the next bit, which is 1. So how many elements we have with bit 1 as set? So this one and this one. Do we have any other element? No, we do not have any other element. And this k, this count, which is a 2, this count 2 is less than k. So it is not possible to have this bit set in answer. So can I decide something? No, do not make any claim here, because if you delete some element, then those elements might be helpful in future. So do not delete any element, because they might be helpful in future. I will only delete the element when I can make the current bit set in answer, because then I can claim the bits the elements whose bit is 0. I'm not going to select those elements in future. So delete it. Cool. Now I will move to the next bit, and this is bit 0, and here the count is 1, and this count is less than k. So you cannot make this bit 0 as set. And yes, now we are done. What is my answer? My answer is simply equals to, this is 2 power 4 and plus 2 power 2. So this is equals to 20. And this 20 is the maximum AND value that you can form. So is it clear to everyone? Just write a quick lesson so that I can discuss the implementation. Yes, no, anything? Cool. So now the only thing, how I can delete the elements. So which data structure I can prefer. So what you can do, you can use a set or or a map, or you can also go with the unordered set or a unordered map to delete the elements from the container. But using set and map is not a good idea, because using set and map will add a factor of log in the time complexity. So let's just optimize this further. And how I can optimize this? So I have to delete some element, right? So deleting some element, I can also say this thing, that do not delete the elements, just make all its bit 0. That is, if I have to delete s2, then I will make all its bit 0, or I can say I will update the value of s2 as 0. Cool. So that it will not added in the count in future. Similarly, I will make s5 as 0. This is similar to deleting the elements. So yeah, this is the complete approach. Now let me just show you the implementation. So yeah, here we have a implementation of the third problem. This is the method that you need to complete. So here first I have taken the size of the array, and then here I am having my array s, or you can say subarray sum vector, where I will store the sum of all the subarray, and it must be of a data type long, because the value of sum can be up to 10 power 11. The number of elements is up to 100, and the maximum value is 10 power 9. So if you have all the 100 elements value as 10 power 9, so in that case the entire array will have the sum equals to 10 power 11. So that's why we must have to use a long data type. Cool. So this is my current subarray sum, and here I'm just simply iterating over all the subarrays, and in my current I will add the current element, and then I will just simply push this element, push this current in my subarray sum array. Cool. And then I have initialized my answer with 0 and iterate from bit 40 and to bit 0. And why here I have selected 40? Because the maximum sum that we have is up to 10 power 11. So that's why 40 bits are enough. Then here I am having my variable count, and count of 0 will simply store how many elements we have in array whose 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 bit is set. So just simply iterate over all the elements of this array subarray sum, and then here I am using the right shift and taking an AND with 1. And if the bit is set in the sum, then after taking an AND, you will have a 1 as the value of val, and then if it was 0, then you will have 0. So here I have just incremented my count by this val. Cool. And if this count is less than k, then I'm not going to claim anything. Just simply skip this and move to the next bit. Otherwise, I can have this bit set in my answer. So I'm just simply marking this bit set by taking a OR with the one left shift bit. Cool. Then again, I'm again going to iterate over this subarray sum. I'm again going to iterate over this subarray sum array. So here now I'm taking every element as a reference. This is a reference variable. It's not the copy of element. It is a reference variable. So if you will make any change, then it will be reflected in the original array. So then again, I'm checking if the whether this bit is set or not. Current bit is set or not, and if it is not set, then I can delete it. So I'm just simply making its value as a 0, and finally I'm returning this answer. Now, what will be the time complexity here? So here the time complexity is simply equals to 40 multiplied by this subarray sum array, this subarray sum, and subarray sum array size. So I can say it is simply equals to 40 multiplied by, this is the time complexity, n, and n plus 1, and divided by 2, and this is the maximum, this is the number of subarray we have, or you can say size of subarray. So I hope it is clear to everyone. And also let me just quickly write the space complexity. So auxiliary space complexity, which is n into n plus 1 and divided by 2. As I have it stored the sum of all the subarray in an array. So now let's just move to the last problem of the contest, which was again a very interesting. So it has very less summation out of around 1k summation. There are only 6.32 percent correct summation. So here you are given an array ARR of integers and with the length n, and a subset of the given array is considered as crazy subset if the max value of this subset is lie in the range from L to R, and this L to R is also given to you, will also given to you, and your task is to find the total number of crazy subset of the given array ARR. And since this answer can be very large, then you have to return the answer under modulus 10 power 9 plus 7. Very obvious. Then here we have a definition of MEX. So MEX of a subset is the smallest non-negative integer that is not present in the subset. And for empty subset, it is 0. So it is the smallest non-negative missing integer, MEX. Now let's just analyze the constraint. The number of elements can be up to 5 into 10 power 5. And their value is obviously gonna be less than or equals to n, because it is not possible to have MEX greater than n. If all the elements are from 0 to n minus 1 in your integer array, then MEX is equals to n. So that's why here it is mentioned that the value itself going to be less than or equals to n. Cool. And obviously the range, since the max is less than or equals to n, so that's why the value of L and R is also less than or equals to n, and this R is greater than or equals to L. So let's just quickly discuss how we can solve this problem. So crazy subset. So I need to count. I need to count the number of subset whose max value is in the range from L to R. So I can also say that my answer is simply equals to the number of subset, the total number of subset with the MXE value as I for all the I in the range from L to R. So summation from I is equals to L and it goes till R. And for every I, if I know the number of subset for which the MEX value is equals to I, then if I add the values together, then that will be my final answer. If I know all the answer for all the I's. Cool. Anyways, so here for every I need to find number of subset with their max. If I know this count, the number of subset with their max equals to I equals to I. So now I have fixed the max value. Now how many subsets are possible? So if you want to have a max as I, then what does it mean? It simply means in my subset we must not have this I, and we must have all the integers. We must have all the integers from 0 to I minus 1 in the subset. So here I'm going to write a general formula, or let me just first give you some example. So let's say the value of I is equals to 5. Then what does it mean? It simply means we must have all the integers from 0 to 4 and in the subset, and we must not have this 5. And for the rest of the integers, I don't care if it is present or not. So we must have a 0 in the subset, we must have a 1 in the subset, then 2, 3, and 4. Then I cannot include 5. I cannot include 5. But what about the rest of the integers which are greater than 5? So rest of the integers which are greater than 5, I can select or not select. It's up to me. So let's say we have a 6, and then we have 8. Let's say 7 is not present, and let's say we have a 9, and let's say then we have a 10, or let's say then we have a 15. And from 10 to 14, we do not have any occurrence of any integer. And there might be the case when you have multiple values, repeating values. So let's just also consider that case. So let's say I have two occurrences. I have three occurrences of 2, and let's say I have two occurrences of 3, and let's say then I have I can say 4 occurrences of 2, and let's say 2 occurrences of 4, and let's say I have 2 occurrences of 6, then let's say I have 3 occurrences of 9. Cool. So in this case, how many subsets I can form? So I know I must have to pick at least one integer, at least one 0, at least one occurrence of 1, at least one occurrence of 2, at least one occurrence of 3, at least one occurrence of 4. But I can also pick two occurrence of 2. I can also pick 3 occurrence of 2. So basically, I can pick any occurrence of any number of occurrence of 2, but it must be a non-zero. Cool. So from here, I can select any subset. Do not get confused. These are the indices. I can select any non-empty subset of indices. So now let me just quickly generalize this. So for here, the number of subset for which I is equals to 5. This is simply equals to 2 power 0, and here not 0 but 2 power count of 0. How many occurrences of 0 we have? So here it is a simply equals to, it is a simply equals to 1. So 2 power 1, these many subset and minus 1, because I cannot include an empty subset, because if you include the empty subset, then your max value is not equals to 5, will not gonna be equals to 5. Then multiplied by 2 power 1 minus 1, that is a count of 1 and minus 1. Then here I can select any subset, right? I can select any subset of these four elements, but that subset must be non-empty. So here I can say 2 power 4 and minus 1. Then and then here I can multiply this with 2 power 2 minus 1. This is for 3. Then 2 power 4 multiplied by 2 power 4 and not 2 power 4. Okay, let me write 3 occurrences of this 4. So here it is simply equals to 2 power 3. 2 power 3, I can select any subset and multiplied by minus 1 and minus 1. Cool. And now I'm not going to pick this integer 5. Otherwise the max would be not equals to 5. So now what about the rest of the integers? What about these integers? So what about these integers? So here I can either pick, or basically I can pick any subset of these integers. So let's just say the count of these integers is simply equals to n, total number of elements in my array, and minus, let's call this as a previous. Let's call this as a previous. How many elements we have previously seen? So here in this case, the value of previous is equals to 1 plus 1 plus 4 plus 2 and plus 3. So this is equals to 11. This is equals to 11. Cool. And then here I can just simply multiply this by 2 power n minus this previous, and I also need to subtract the count of 5. So count of 5, or I can say count of I. So this value is equals to 8, or yeah, this value is equals to 8. We have 8 integers here. We have 8 integers here. So now here I can select any subset of these 8 integers, either it is empty or non-empty. So yeah, this is my number of subset for which the max is I. So I hope it is clear to everyone. And if at any point of time, you know that we do not have any integers, we do not have any occurrence of 5 in my array. So in that case, you need to immediately return the answer, because if you do not have 5, then it is not possible to make max as 6. It is not possible to make max as a 7, 8, or any integer. If you do not have a occurrence of all the integers from 0 to I minus 1, then it is not possible, right? So let me just quickly write the general formula, and after this I will just simply discuss the implementation and wrap the session. So answer of I. So this simply means the number of subarrays, the number of subset whose max is equals to I. So here uh, the formula is 2 power count of 0 minus 1. The number of subset, the number of ways we can select any combination of 0, and such that it is non-empty, and multiplied by 2 power count of 1 and minus 1, and up to 2 power count of count of I minus 1 and minus 1. Now I cannot pick integer I. So, and what about the rest of the integers which are greater than I? Greater than I. So I can select any combination. So this is 2 power n minus previous, the previous integers that I have seen, basically the count of all the integers from 0 to I minus 1, and minus the occurrence of a current integer I. Occurrence of a current integer I. So let's say count of I. So this is my answer. These many subset we have. And there is an edge case. If at any point of time, you realize that a count of I is equals to 0, then after return, then immediately return the answer. Immediately return the answer. But make sure to first calculate for this I, and then check if count of I is equals to 0, then return answer. So in this way we can solve this problem in logarithmic time. Why it is logarithmic? Because here I need to find the power. So to find the power, I can write the binary exponentiation logic to find the power in a logarithmic time. So this is my power function using which I can find the value of a to the power b under modulus m in just a logarithmic time. Then this is a method that you need to complete. And here we have a variable constant. Here we have a variable mod, constant variable mod. And then taken the size of the array. Then this is my unordered map. And here I will store the frequency of all the elements. Then this is my answer. And here I have initialized my variable current with 1. This current will simply store this current will simply store this value. This current will store this value. And I can build this current in a progressive order. That is, before moving to the index I plus 1, I will just simply multiply. The value of 2 power count of I minus 1 and minus 2 power count of I, not I minus 1. Count of I and minus 1. Because to have integer I plus 1, as a max, you must have all the integers from 0 to I. You must have all the integer. So this was my previous current. And now I have added I have multiplied 2 power count of I minus 1 in the current. So now I am building this in a progressive order. Cool. So then here I have my variable previous that will simply store the number of elements we have processed previously. So first I need to iterate from I is equals to 0 and up to L minus 1. And if at any point of time, the I get that frequency of I is 0, then I can immediately return the answer. I can immediately return 0, because it is not possible to have to select any subset whose max is in the range from L to R, because some integer from 0 to L minus 1 is missing. Otherwise, I will add its frequency in a variable previous, and I will multiply 2 power count of I and minus 1 in my variable current, and then I will take a mod. Cool. And here I'm subtracting minus 1. That's why here I am adding mod. Then I iterate over all the integers from L to R, and this is my current value. This is my value of here. How many subset I can select with the max is equals to I. So this is simply equals to current multiplied by n minus previous minus count of I. Super simple. And I take a mod. Then here I am taking a mod and adding this value in my final answer, and then taking a mod of this answer. And if I get that the frequency of I is equals to 0, then I will immediately return the answer. It is not possible to have a max greater than I, because I is missing. And then adding this frequency in the variable previous, and before moving to the next element, I am adding this in the variable current, that is multiplying 2 power count of I minus 1 in my variable current, and then take a mod, and finally I am returning the answer. So this is the complete explanation for all the 4 problems. And also one more thing, you can find the solution of all the 4 problems on my GitHub repository. So let me just share the link in the chat box. Otherwise, you can also search my username, which is Ayush8303. So then you can go to this repository, post contest analysis, and here after and half an hour, I will create one new folder, and with the name GFG Weekly Contest 187. So yeah, you can find all the solutions in this repository. So yeah, this was all for today's session, and I hope you have learned something new and enjoyed the session. So in case if you are having any doubt, then just go ahead. Otherwise, we are good to wrap the session. And make sure to hit the like button if you have learned something new, and also write down your comments so that I can improve the sessions and the problem set for all the future contest. So I guess no doubt at all. So let's just wrap the session here. And thank you so much, everyone, for joining the session, and have a good day.